My name is Dr. Julia Kazmaier, and I will be leading this Introduction to Agent-Based Modeling for Social Scientists webinar today. Thank you very much for joining. This is the first of a series of 3 webinars on agent-based modeling. So today we have the introduction. In 2 weeks we will talk about adding real-world data to agent-based agent-based models. And 2 weeks after that we will talk about setting up automated experimental suites and dealing with model output. So to start off today, just let you know, we'll begin by discussing top-down and bottom-up problems and problem solving. Then I explain the difference between some common kinds of agents that you may be aware of. I'll pay most attention to agent-based models because that's what this webinar is about. Following that, I will walk you through an agent-based model that I built of the telephone game. And then we'll wrap up with some pros and cons of agent-based modeling in general, as well as some specific platforms, languages, and resources that you can use if you want to start agent-based modeling within your research. I then summarize the whole thing and give you the option to ask me some questions. You can actually ask questions at any point during the webinar if you type them into the questions box, but I will only answer them at the end. So to start, top-down. Top-down problems are problems that can be effectively solved by top-down problem solving, and that is incredibly tautological, so I will be a bit more specific by telling that top-down problems can be understood as top-down if they occur within a system that is or can be understood as whole, that is well understood, that has centralized control or structure. So typically, top-down problem solving is about reducing a system to its component parts. So the cause of the problem can be isolated within a part of the system, or maybe within specific interactions or a specific area. And top-down problems can be effectively solved by identifying causes and repetition, prediction, hypothesis, the kind of classic scientific method approach that we think of as problem solving. So a really typical example of a top-down problem is if an engine goes clunk. Now a mechanic who, unlike me, would understand an engine quite well, is able to treat an engine as a simple, linear, reducible, and non-context dependent system. So they can take the engine apart, they can ignore lots of the engine parts that they already kind of understand are not likely to be going clunk, and they can ignore the rest of the plane, the rest of the planes in the squadron. They can even ignore things like fuel and replacement parts for an engine. They definitely do move in and out of the engine. They're only temporary parts of it, but because they're quite predictable and limited, they can just ignore those. Another example is a prosthetic leg, especially if we compare that to a non-prosthetic leg. The leg has clear boundaries, it is well understood, it has relatively linear behavior. Unlike the non-prosthetic leg, it won't perform differently from one day to the next, depending on what the person who uses the leg ate for dinner last night, or how much sleep they got, or how they're feeling, those kinds of things. Third example is wind tunnel testing, and this really demonstrates that seeing a problem as top-down or not is a matter of perspective. A wind tunnel, the motion of air, of all the air molecules in a wind tunnel, is incredibly complex. But if the tunnel is well designed, then you can kind of treat those molecules as a stream, and they're simplified, and you can really sort of control the situation. It becomes very top-down if you want it to be. So in contrast, bottom-up problems are those problems that are effectively solved with bottom-up problem solving. Again, that's not very helpful. So I will tell you that a problem is bottom-up if it occurs in a system that is open, ill-defined, dynamic, where control is diffuse or partial or constantly changing. In this case, the same things that produce a problem one time might not produce a problem another time. It's really hard to predict. Bottom-up problems tend to be about identifying and top-down problems are about identifying and removing a problem, whereas bottom-up problems tend to be about understanding how the problem arises. This is because we can't assume they're reducible. We can't take them apart, essentially. We can't assume they're linear. They don't behave the same way a certain amount of input does not equal a certain amount of output, then very time and context dependent, and they're very open and complex. And it's a bit of an issue that bottom-up problems often seem to be baked into the system rather than sort of introduced. So something might get into an engine and make it go clunk, but bottom-up problems are sort of inherent to the system, and we have to understand what it is that's causing them and how else we might build a system that doesn't have those things. So we usually do that by recreating the bottom-up problem through deterministic low-level rules, finite parameters, and varying, including extreme or counterfactual conditions. And these kinds of systems are harder to apply the classic scientific method for, because classic scientific method things like isolating the system and repeating the experiment lots of times don't really work if a system is not reducible or not repeatable. It's just a bit of an inherent conflict. Now, a very typical example of a bottom-up problem is a traffic jam. And this is because, there are many vehicles that more or less follow the same rules, but whether or not they cause a traffic jam is not always very easy to predict or prevent or manage. They're definitely not top-down, because if we try and take the traffic jam apart by taking all the cars apart, the traffic jam disappears. So it's just one of those things that you can't isolate the jam. There's not one moment of jam in there. And instead you have to treat the whole system, the roads, the vehicles, the junctions, even the weather, things that happen to be on the side of the road that day, everything contributes to whether or not there's a jam. Traffic jams are also quite open systems. Vehicles enter and exit, but the jam might stay there, even though all the vehicles are different. Or the jam might travel backwards, even though that means the jam is approaching vehicles as they approach it. There's all kinds of strange behavior with traffic jams that would make it really not as well understood as we liked, not very linear, not very consistent or predictable. Another example is earthquakes. They're really hard to predict, and it's really hard to predict when they happen, how big they'll be, exactly where they'll be. There's just a lot of factors going on, and we don't quite understand it very well. A third example is castilleries, or human pyramids. And we know that there's lots of people that participate, and they practice a lot, and they'll have a shared motivation, but the actual success or failure of a given attempt is really hard to predict. It just comes down to a lot of things, like who had an argument 2 weeks ago, or what the weather is like today, or how far they had to travel in order to get to the competition. It's just really unpredictable. The key issue with all of these bottom-up problems is that they're very non-intuitive. It's just really hard to have good instincts about exactly where a traffic jam will form or dissolve, when an earthquake of a given size will hit, or what place a given Castillaire's team will take in a competition. So that is a very brief exploration of the difference between top-down and bottom-up problems and problem solving. So next, let's look at agents. By agents, I mean representations of things that take action. I don't mean spies. And the first that you might be familiar with is artificial intelligence. And a clear fictional example is the Terminator. These agents are often physically embodied, generally autonomous, individual, and relatively independent actors that go about solving a variety of problems or creatively solving a problem in a variety of ways. Second, you have multi-agent systems. Real-world examples of this include drone swarms, like you see here, these little robots trying to cross a road. Linked traffic signals can be multi-agent systems. Even the complete set of smart lights and smart speakers in your house might be wired together in a multi-agent system. They use distributed control and typically strict rules to solve a limited number of specific problems. Third, and the most important for us, is agent-based models. These are usually simulated rather than embodied. They have multiple agents that interact with each other and the simulated world according to rules. They may or may not have a shared goal, and they are particularly useful for representing certain kinds of bottom-up problems because when intuition fails, computation can take over. Okay, so I'm now going to walk you through more details about agent-based models. I won't pay any more attention to artificial intelligence or multi-agent systems. And I will use an example model that I built for demonstration purposes of a childhood game called Telephone, although you might know it as Chinese Whispers. I chose this example because it's fairly simple and probably most of you will know it, and it also has some non-intuitive features that we can explore with an agent-based model. I will use text and images as we move through sort of exploration of the telephone game. So agent-based models have a simulated world of varying richness, including time. They have objects or agents, and they have states and rules. So I'm going to dive into each of these and give you some examples in the game called Telephone. Okay, the world can represent just about anything. You can try to represent a stock market, you can represent the city that you live in, you can represent the room that you happen to be in now. That might not be particularly enlightening, but do what you like. The world also includes time, and because this is a computer, it has to advance in discrete time steps. Computers haven't really cracked continuous time yet. And the world that you will build to address whatever problem you're interested in should include representations of the potentially interesting factors. So if you're trying to model a stock market, you probably want to include current selling prices. If you're trying to model a city, you might want to include weather. If you're trying to model the room that you're in, maybe capacity is a valid feature that you're interested in modeling. The world is also unique for each agent in it, as that agent's world contains everything else, including the other agents. So although my world, if I were an agent, and the world of an agent who sat right next to me will be very close, they're not identical. That may matter in your model, depending on whether you're including factors like perspective or experience. And the states are composed of the features of the world, the contents of the world, and they may be affected by, or they can affect agents, objects, the world itself, random factors, all these other things according to rules. I get into rules in a moment. So just to give you a brief look, this is the world of the telephone game. It's quite simplistic. This is built in NetLogo, which automatically generates a world that has a playing field of given dimensions. You can change those dimensions as the model if you choose, but it comes up with a sort of basic one if you don't make any changes. It has a number of agents scattered across the field, and it has a noise level, which you can see here on the left-hand side. And when I built this model, I could have included more features in the world. I could have included things that generate the noise, or I could have included colored fields to represent maybe neighborhoods or streets and pavements and things like that where the agents might be physically located. But they didn't seem particularly relevant, so I left them out. And so they're all just living in a world of utter darkness. Now the agents themselves, again, can represent most anything. I mean, intuitively, we think maybe they should represent people, but they could represent cars, they could represent companies, ocean waves, nations, anything you think is worth representing as a decision-making kind of actor. They have, like the world, they have representations of interesting factors. So, for people in a stock market, that might be how much money they're earning. For people in a school, if you were trying to represent behavior in school, age might matter. Color, speed, height, location, any of these things. Typically with agents, these are all often quite dynamic. So, how much money a person has changes all the time based on their income, their expenses, and their behaviors. The agents are all unique and behave uniquely, even if you have two agents with all the same money and color and speed, and they're located in the same place, they will still have unique ID numbers, and the computer will recognize them as unique and potentially call them in a unique order. That may matter to your model and may not. Like the world, the agents have states that is sort of the sum of all of their features, and they are affected by their world according to the rules. And basically what they do is they make decisions and they take actions, which includes no action, that is that is considered in action in agent-based modeling, based on the world, the states, the rules, what other agents are doing, lots of things. So here's a quick look at some of the agents in the telephone game. I have selected this little one here and inspected him, which means that I've called up this sort of list of all of his features. So you can see he has an ID number, which is called a who. He has a color, a heading, a location, a shape, all of these things. He's got a prize count, 13, so that's particularly important for the telephone game, and I'll explain a bit more about why in a moment. You can also see the world state here, because you can see sort of the noise level and the total prize count, so that's a bit relevant to the world, because states are basically the sum of their features. So the world has a state, the agents have a state, they can change all the time, some of or all of it can be quite static. And these can be things that can change dynamically based on things that you give or the agents give to the world or other agents. They can also be outputs, so you can have the world report to the agents, or you can have the agents report to each other. You can also create output that you essentially say is a model of record behavior within the model. And the states are how agents use, they're what agents use to make decisions about what they do. So for example, an agent might look down at itself and say, oh gosh, I have a prize count of 13. In that case, I should be doing this. You know, in this particular model, he'll look down at his prize count and say, oh gosh, that's how I'll determine what color to be. But we'll come on to that in a moment. So just a quick look again, here's the sum of all the features can be understood as the agent state, and the sum of all of the sort of world features can be understood as the world state. The last one is rules. Agents use rules to govern how their states change or how they make decisions. They can use model-generated info. They can use information that the modeler gives. They can also use randomness, and they can be simple or complex, so they can take the form of if, then, while, for each. And I'll just point out a couple. This is some of the code of my model, and you'll notice it says, if, else, the length of current turtle equals 0, which you don't need to know the exact reason behind that, but that means if no turtles are currently playing a game. Agents, for some reason, are called turtles in NetLoader. If no agents are currently playing a game, then start new game. Or, if agents are currently playing a game, wait, play game. So you have to see, if nobody's playing, you start a game. If as many people are currently playing as is allowed in a game, then you end the game, otherwise you play the game. So they can be quite complex structures. And here we see, to start a new game, you ask the turtle, you say, whoever's playing to 0, and you say you can choose a new starter randomly according to whoever has the most prizes or least prizes. That's a feature that the modeler decides to set. So I'll just come on to the interface tab and I'll show you here, choose starter, most prizes is currently set. So that's something that you can determine how you want the game to run. So just briefly, this is the interface tab. This is what a NetLogo model opens to. The interface here, you'll see setup, go. There's the slider that lets you go faster, slower, if you want to look at it a bit more clearly, save the file, these kinds of things. The info tab, the next tab over, is good practice to fill this tab out completely, but lots of people don't. This is how you explain the logic of the model and what it's about and why people should be interested in using it. And finally, the third tab, is the code tab. And so we saw a bit of this before. This is what NetLogo code looks like. You can see that it's more or less clear English. It has things like, set noise level to a random number under 100, if layout style is random, layout the right turtles randomly. It's got these sort of fairly logical phrases and structures, which is quite useful if you've not done a lot of coding and you want to learn how to code in NetLogo. And let's move forward. In this is a video, and I just want to show you how to make some modeler choices. So first I want to point out that this model is set to garrulous. You'll see on the right-hand side over here that it is set to garrulous, which means that it runs slower than it needs to, and it writes out lots of steps down here in the command center. So you can see what's going on with the model more or less in real time. There's also game layout. You can choose between circle and random. And here's the choose starter, as I mentioned before, randomly, most prizes or least prizes. And choose next. There's a few more options here, but I'll choose randomly again. So these are things that the modeler can decide when setting up the model to run, how that model, what kind of rules that model should use, essentially. Okay, the next short video is about sliders. These are the sliders also here on the right-hand side, where you can set the number of players, so that's how many people are playing in the world, how many players per game. Again, you can also switch applying noise distortion on or off, and there's the current noise level, and so that determines whether or not that noise level will affect the players. So you can set at what level that noise level has to be before it starts interfering with players' ability to hear. So the next short video I have is called Set Up and Go, which you might be able to predict what it does because I hit the setup button, and what that does is it creates, because I chose layout circle, it moves all of the agents into a circle. I then hit go once, and you can see it's doing some of its chatty stuff here in the command center. Hit it a couple more times, and you'll see that players are selected from the edge of the circle. They move into the middle, and then they sort of whisper to each other. So if you're not familiar with the game, which I expect you all should be, but just briefly, the game starts when one person picks a word, whispers it to someone else, who then has to whisper what they think they heard to the next person, and so on. So if we look at these circle, the ones who played are pale green, and there's the prize count is 20 because they succeeded in all whispering the same word. The person at the beginning of the line and the person at the end of the line had the same word. Now this isn't always true, especially if I apply noise distortion. So let's see what happens next when I do that. So this one, I'm going to change the noise distortion level, the acceptable noise level, to be much lower. So that means whatever, that it's almost certain that the current noise level will cause interference and make the agents mishear each other. So this time, when they're whispering words to each other, they're similar but not exactly the same. You can see that it was just too noisy because I set the noise level so low. The first player whispered D3D, but the player 4 heard OGD. Still, a small prize will be awarded if any of the phonemes match. So that means since there were 4 players and they had one letter in common between the first and final words, there were 4 prizes awarded. Now I can keep hitting go once, and just march through another game. This time, no letters are shared between the first and final words, and so no prizes are awarded. That's a terrible shame for them, but it's just too noisy. Now it's a little bit tedious to hit go once every single time. So in this video, you'll see that you can turn off the garrulous function so that it runs faster and then it just doesn't sort of print out things. And you just see the players just smashing through game after game after game. Sometimes, because you can see the total prize count going up, they're winning. Sometimes they're not. It's just how the game ends up going. So you can turn the Go Forever button off by hitting it again. And that's very useful because you're trying to simulate things that maybe you want the agents to play 10 million games. You do not want to hit that Go Once button 50 million times, once for each player in the game and once for wrapping up the end of the game. You know, maybe you want to see what the game looks like after 1,500 time steps. So just this one's just a picture, it's not a video. You'll see that there are lots of different colored agents around the edge of the circle. Total prize count is quite high. Current noise level is 0, so it's very quiet despite so many people having won. And this sort of distribution of colors, because color depends on their prize count, so they change color when they win a prize. So the distribution of color demonstrates that there's a distribution of prizes. And again, if I skip forward to 4,000 time steps, again, the colors have all changed. The prize count is much higher. Current noise level is 205, so it's very noisy right now. And you'll see that the distribution of colors not only has shifted, but is also much flatter. It's much more spread out. And that's an interesting thing. It's not something that I would necessarily have predicted about this game. So you'll say, okay, great, we can, you know, replicate a childhood game. That's really valuable, I'm sure. But why would you want to do that exactly in an ABM? Why does this matter for social science modeling? Well, because some features of this very simple game are not very intuitive. You know, it's just not clear how the color distribution or the histogram of colors is going to look at 1,500 time steps or 4,000 time steps or 10 million or 1 million time steps. And then how does it compare if we do 1 million time steps when we choose a different way of choosing the starter or the next player? What about if we have all the rules stay the same but there's twice as many players? How about if the vocabulary size changes, or we do or don't apply noise distortion? If we take noise distortion away, every single game will win full prizes, but what does that mean for the color distribution? It's just not clear. It's just not intuitive about what that's going to do. So that's where agent-based modeling comes in, because there's no need to rely on intuition for complex behaviors like that. You can just build a model and test it. You don't have to say, I think I know what would happen. You can see. Agent-based models are also extremely useful for formalizing the mental models so that others can inspect them. Essentially, your own intuitions about what you think happen are mental models. And you might be absolutely confident that you know what's going to happen, but unless you can formalize what you think in a way that someone else can inspect, then you're just going to really struggle to convince them that you know what's going on. But if you can put it in a model and they can look at the code, then they either have to be clear about why they have a problem with your thinking, or they have to agree with you. It's very powerful, that. They force abstract concepts to be represented concretely. So in this case, you know, we're awarding prizes based on whether or not people can hear a word. That's not particularly relevant. But it's not a million miles away from how we maybe award prize social value in life to people who hear rumors, or, you know, whoever has all the gossip, whoever knows all the business, or maybe even something, you know, less sort of moral, like, you know, ethically judgy like that. Maybe just someone who has who gets access to all the information on how to build a good presentation, how to, you know, apply for grant money. Are they going to get more rewards because they are better at taking in information? Maybe we can test that. Agent-based models are relatively cheap and easy, and they can test the untestable. So in this case, I could test a game of telephone with, you know, a dozen people maybe, but it would cost a bit of money to pay for their participation and to hire a room and to some kind of white noise machine. But if I wanted to run a game of telephone with 1 million people, I would not be able to get the funding to run that. But I can easily ramp this model that took me some hours to build, and it'll take some maybe hours to run, 1 million games with 1 million players. And that is a whole lot cheaper and easier in simulated form. Also, things that are untestable because they're unethical or morally difficult. You know, it's, if we have a reason to think why someone's behavior is poorly influenced as a result of problematic upbringing or poor nutrition or something like that, it is unethical to just deprive people of good upbringing or nutrition in order to see if our theory is correct. But you can deprive computer agents of metaphorical nutrition to test your theories. It's possible. They're potentially very fast. I can run 1 million experiments overnight, maybe, depending on the complexity of my model. They can show a range of possible futures. I mean, if I were to run 1 million experiments of a telephone game, I might find that certain sets of features always lead to a normal distribution, but I might find that other sets of features commonly lead to a normal distribution of colors, but occasionally lead to a bimodal distribution of colors. And that's valuable to know. The real world only happens once, but a simulated world can happen millions of times, and you can see how often something does or doesn't come out of those. You can use real data, so you could put real stock market prices into a model if you're trying to test some kind of stock market theory. You can use training data, random data, lots of other things, and you can run them again and again and again, with or without changes. So you can really, unlike the real world, get a very complex situation back to zero and start it again to see if it comes out the same. They're very intuitive for non-specialists to understand. We kind of all understand a simulated world where agents do things and make decisions and take actions, and that is useful to explain. It is not as easy to explain some complex theories, but because there's a visual element built into this and a sort of social element built into this, people tend to get it very quickly. There are also cons to agent-based modeling, and I'm going to tell you about them too. The mental models and the agent-based models based on them are very hard to be critical about. You will find that people are just very protective of how they think it happens, and they're not always willing to test or even fully explain how they think it happens in order to build an agent-based model. So some people, it's just really poking a sore spot to make them build a model. Concrete representations that you need to get a computer to understand what you're talking about are not always good ways to represent abstract concepts. So you might, in your model, have to designate trust as a value between 0 and 100, but that probably doesn't really capture what people mean by trust. They know about more or less, and the relative concept of trust is in there, but that, it's deeper than that. But because agent-based models are so fast, people often want to use them for prediction. They think we can create a world that is a mirror of our world, and we'll run it in the future and it'll tell us the truth, and that is not how agent-based models work. They create a mirror of what we think about our world, not the world. And possible futures are really hard to turn into risk profiles. The idea that 90% of the time the telephone game gives us a normal distribution and 10% of the time it gives us a bimodal distribution, that is hard to turn into a risk profile. Do we want to avoid bimodal distributions? Do we want to seek them out? Are we fine if they happen, but we have to make sure something else goes with it? They're just really hard to think about. Because they are made with computers and people kind of intuitively understand about motivations and interactions and simulations, they can give a real sense of security and truthiness. People believe them rather than treating them like the output of other kinds of models. Then people intuitively would say, right, okay, that's what your results say, but let's have a critical look. People sometimes just believe computer results. At the same time, some people just don't believe computer results. They say it's made with computers and therefore it's a dang lie. And, that is just hard to overcome sometimes. And they are easy to misunderstand because, the real world observations of some kind of pattern of interest are filtered through mental models and then through an agent-based model and then through an exploration of that agent-based model. And we might think we know what's going on and we just have it all backwards, and we are not always well equipped to see that. So that is a risk. So if you are interested in learning about agent-based models, I'll tell you a bit about platforms and languages. There are lots of agent-based modeling platforms available. Almost all of them are free. They are open source. They are relatively small programs to download. And there are tutorials and information and question and answer fora on the web. Mason is an example that is easy to learn, but it's not particularly well recognized. Repast is really powerful, very, very professional, but it has a steeper learning curve. NetLogo, which I've shown you today, is very middle of the road in terms of power, but because it has the built-in visualization, it is very useful. It is also sort of a English-ish coding language, so it's fairly easy to learn. EM Lab Agent Spring is a great one that's built by some former colleagues of mine. It's modular, which means you can sort of just borrow other people's code and slot it into your model without having to do a whole lot of complicated coding and testing. But it is a bit industry specific, as in it's focused on modeling industries, electricity and production and manufacturing, and it's not that well recognized outside of those fields. You can also, if you're a whiz at programming in Python or something like that, you can just use object-oriented software. That is extremely powerful, but because it's not targeted on agent-based modeling, you will find it harder to find examples of code that you can use as the basis for your own work. It's harder to find answers to the questions that you might have. Wikipedia has a couple of good resources. They have a comparison of agent-based modeling software. They have history and uses of agent-based models. And there's also my code if you want to download this telephone game and have a play around with it, pull all the levers, push all the buttons, see what happens. You are more than welcome to. And this link will be available to you shortly after the webinar if you want to find it. I'll tweet it out on my Twitter. So to summarize, bottom-up problems are non-intuitive, large-scale effects as a result of many small acts. Agents are heterogeneous actors that observe and decide and act. Agent-based models are a bottom-up simulation with easy testing capacity. In their favor is that they can be inspected, they are cheap, easy, fast, and they can do impossible experiments. The cons is that they inevitably simplify complex concepts. They are often misused for prediction, and they are easy to misunderstand. So now I will open up for questions. Can agent-based models help to identify key drivers, factors of agent behavior? Yes, they can. Ideally, you would have some sense of what might be a factor, but yeah, if you have a whole bag of things and you think, I just don't know which of these matter, then you can build a model with all of them, play around with setting them at different levels and setting rules slightly differently, and keep testing until you're able to recreate a behavior in the model that you think replicates the behavior of interest in the real world. So for example, if we were trying to build a traffic jam model, I would definitely need a number of cars. But I might say, okay, does the size of the car matter? Does the height of the driver matter? Does the color of the car matter? I don't know. Build a model with all of them and then do a parameter sweep to see which ones matter. I will cover that in the third part of this series, parameter sweeps and experimentation. Okay, we have another question. Someone has written in to say they are wondering whether there's any consolidated default rules of behavior. I would say, if I understand that question a bit, if there's a default rule of behavior, you have to devise it yourself based on what you think your model needs. There's no standard sort of behavior. You might be able to borrow someone else's modeling code. So if you have a model that is about traffic jams and you think, actually, I don't want it to be about traffic, I want it to be about shipping or freight or something like that, you might be able to borrow some of those rules, You might say, okay, people behave in an ordinary way. They adjust their speed based on things ahead of them and the size. You know, there are some situations where there are relatively standard sort of rules, but ideally every model will have your own. Which disciplines tend to use agent-based modeling? That one's difficult to say because lots of people use it for lots of different things. You can model ocean waves if you're an oceanographer. You know, if you're someone who's looking at material flows, you can model things that flow. I have certainly seen it used extensively in engineering and industry and manufacturing because people want all of the different working parts of machinery and the people that interact with them and things like energy networks and things like that. They want to be able to model those complex situations. Absolutely popular in certain kinds of social sciences as well. I have a history of studying the evolution of language, and so because it is unethical to just stick babies in a dark room and not teach them language and see what happens when you suddenly start gabbling at them. We do it with models instead. And so, yeah, there's really psychology and game theory and mathematics and engineering. Lots of different people use agent-based models. There's no right or wrong way to do it. Can you give some concrete examples of social science research questions answered with ABM? Yes, I can. There are questions like how people decide whether or not to go out tonight. That was a very famous model, and it dealt with people's past experience and how pleasant they found their environment. So they had sensors for things like how many people were around them and what the noise level was and how crowded they felt. And they would develop a history of association. So that place is always crowded. I don't want to go there. This place is always really quiet. I like it. But every single person in that model had a different standard for what they felt was the right kind of crowded. And you can see, you know, crowds of people moving and swaying and adjusting as each one got over its tolerance and left, and then someone else said, oh, this is too quiet, I'm going to go somewhere busier. You got interesting patterns. Economics is another really popular, I think economics is social science, but some people might argue. But yeah, exchanges and trades and negotiations, these are all things that have been answered really extensively with agent-based models. Supply chains is another one because you can have agents that take inputs, you know, like recycled plastic, and they'll turn it into outputs like pellets for recycling, and they'll give that to someone else who takes the pellets and makes, you know, bracelets or handbags or whatever it is that people make out of recycled plastic. And, you know, you can sort of see materials flow around as the network adjusts and ships things. Does it give you any statistic that shows how much the factors you've included in the model help to explain the outcome? This entirely depends on how you set up your model. It's unlikely to give you that kind of statistic in the interface, which is what I've showed you today. But that is the kind of factor that you could easily find in your analysis, the analysis of experimentations. That would come in part 3 of this webinar series. And that would show you, so if you ran, using my telephone game example, if I ran 1 million experiments with random starters, most prize starters, and least prize starters, probably we would expect the distribution of color to be different for each of those. Now, if I combined that with a factor like noise distortion on or off, I would then have a set of 6 possible experiments, each of the 3 kinds of starters, and noise distortion on and off. So I run 1 million experiments for all 6, and I analyze the results, compare them. It would show whether or not, you know, random made a difference as compared to random with or without noise distortion, or whether noise distortion was immaterial, or whether it heightened the same patterns that we saw as different between the others. There's all kinds of different things that would probably come out in final analysis. Okay. In object-oriented software, as I mentioned, a class instance can represent an agent and methods can represent interactions. Do you know if there's any kind of similar representation model best practice in non-object-oriented models like R or MATLAB? I am sure someone has done it. but I would think that it is much more irritation and time and effort and crying late at night because your code won't work than is worth it. I mean, if you're dedicated to not learning Python, I suggest NetLogo or something like that. Yeah, I don't think non-object-oriented software is very compatible with agent-based models, but I'm sure someone has tried it. I wouldn't advise it, but I'm sure someone has. Is there any community sharing interactive agent-based model-related social sciences? Absolutely. The link that I posted my model code to is, it's got a new name called Cosmos or something like that, but it used to be called OpenABM, and you can still find it under openabm.com, I think, possibly .org. And people just upload their models, and they tell you, what platform it was built on, why they built it, whether it's associated with any published research. You can search by keyword, you can search by platform, you can search, lots of different things, and you'll see great examples of people, using agent-based models to track how people travel through a city, or how products move around in supply chains. There's some really interesting stuff. And some of those will be explicitly social science, and some will be tangential to social science. So again, things like supply chain models, you might think, oh, that's a business question, really. It's not a social science question. But it matters if you're trying to look at how disadvantaged people can or cannot get access to the supplies they need to run a business. So it all depends on your question, your research question. What reading would you recommend to get started? Ooh, I will tweet this as well, because I helped write a book called Agent-Based Modeling for Socio-Technical Systems. And there is a theory chapter all about why complex systems are best addressed through sort of bottom-up thinking and bottom-up problem solving. But there's also a practice chapter which has a 10-step guide on how to build and test and run agent-based models. So if you're interested, I can absolutely tweet you a link to that. And I can even tweet you a copy of the relevant chapters if you ask me directly, because I don't think it's not something I can put on open access platforms. Which disciplines tend to use agent-based models? I think I already answered that, but yeah, everything that has things that do things can benefit from using agent-based models. And what would some repetition of a behavior-based model with the same puts give different results? Maybe you misunderstood. Yeah, well, it depends on whether you have any randomness built into your model. Even if you have very little randomness. So I had the option of choosing who starts a new game of telephone randomly from the entire set of agents, or semi-randomly from only those agents that had more than average prizes or less than average prizes. Both of those still included some randomness. So there was also randomness in the noise level, there was randomness in each individual part of the word that agents whispered to each other would be affected individually by sort of a coin flip about whether the noise level was a problem or not. And you can save your starting seed. This is a bit more technical, and I can cover this in the experimentation, the third part of this series. You can save your starting seed, and that will rerun your model exactly as it ran the first time. If you do not save your starting seed, but just run the model with the same rules, same parameters, same settings, then it will run with some randomness in it. That means agents might be called on in a different order, or agents might be placed in different places on the field at the beginning, and that might have an influence on where they end up and how they're chosen. So you can run a model exactly the same as it was, or you can run it semi-randomly to get some variation. Usually that's important because there are a lot of things that we want randomness for. We don't believe that we have it all figured out and can recreate social science situations exactly. So it's important that there be some way for things to be a bit different each time. But if you don't want that, you don't have to have it.